Is Math 313, number theory, lecture 30. We were just talking about domino stacking, so before going back to elliptic curves, I'll just mention a really nice example of how sometimes the optimally best strategy is not to do everything locally best. And so I've actually met the dog who was used for this, for a series of papers, Do Dogs Know Calculus? So imagine you in the water, you have an intelligent dog, and you throw a stick a little bit to the right of the dog. What path will the dog take to the stick? Good. You're at least as smart as this dog. The dog is named Elvis, by the way. Now let's say you throw the stick a little bit further. What path will the dog take? Still straight. Throw it up here. Still straight. Throw it all the way down here. Still straight. No. This dog knows calculus. If you throw it sufficiently far, the dog knows it can run on land faster than it can swim in the water. And the dog will take the time to go down, run on land, and then come back up. Now, if you look at any moment in time, if your strategy is, I'm going to do at any moment in time what is locally best. Locally best is swim straight for the stick. For a small smidgen of time, that's going to be what will decrease your distance to the stick the most. This is a wonderful example that what's locally best is not always globally best. And the angles depend on how fast the dog runs. If the dog ran infinitely fast on land, this is not, of course, going to happen in the real world, but if the dog ran infinitely fast on land, what would the dog's strategy be? I'm sorry? Straight. Yeah, go straight down, run, and then go straight up. So as long as the sum of these two lengths is smaller than the distance in the water, that's the path the dog will take. If you then shrink it so that these are exactly equal, then the dog is indifferent between the two. And this leads to a bifurcation behavior. That as soon as you go beyond that critical stretch, your path goes through a remarkable transition in terms of what it looks like. I'll post the papers. You can actually prove the arithmetic mean, geometric mean by looking at something like this. There's a lot of terrific mathematics behind this. Interestingly, the file from the first class, it's still trying to copy it, which is fascinating given that the iPad is now quite a distance away from the laptop. All right, so we're going to continue our stuff on elliptic curves. And so what I want to do is I want to talk about how you would prove the group law, and then I want to talk about why we might care about elliptic curves and give us a specific example. So we've talked before about the point of infinity. Group law for elliptic curves. So I will draw my elliptic curve like this. I might have an elliptic curve that has only one component. And we talked about the one-point compactification of the plane. We talked about the point at infinity. So my very first postdoc was at Princeton, then I went to the American Institute of Mathematics, then I went to a large research institution. Who remembers the name of that large research institution? Four words and it begins with the. The Ohio State University. I did not go to a or an Ohio State University. I went to the Ohio State University. There is the point at infinity. It is not multiple points at infinity. There is one. And when you think about it as a sphere, and the North Pole, we plant our flag of infinity. All these points in the plane, as you get further and further, when we do our stereographic projection, when we come up here, they're all approaching the same point. There is one point at infinity. Anybody know what yesterday was? May the 4th. Yes, excellent. It was May the 4th. And so my daughter decided that she wanted to watch a Star Wars movie to celebrate. We didn't have the one where Anakin becomes bad, so we ended up settling for Return of the Jedi and the cute Ewoks. And so we're just at the point now where all the battles are about to happen. This is like the Force, it's all around you. The point at infinity, it is everywhere. No matter which direction you go, it is there. Okay? There is one point. We need to define a group law. We've defined the group law. If I give you 2 points, P and Q, we add them, and then we reflect. And P plus Q is down here. So what I want to do is I want to convince you that this is a group law without proving that it's a group law. So we need 4 conditions for groups. A group needs 4 things. You also need the elements, but I'll assume we know the elements of the group. What's the first property you want for a group? And for our addition law, what's the first thing we need?
Non-empty.
So there is argument as to whether or not a group has to be empty. So it has to be non-empty. Now they do have as one of the definitions of a group that it has an identity element. But how is it phrased? There is an object such that for every element in the group, if you add the identity to it, you get the element back. If the set is empty, could it still be a group? There's not much you can say about the empty set. So let's agree not to talk about the empty. But sometimes it's useful to say that there could be nothing. Maybe there are no rational points on the elliptic curve. So if we look at the group of rational points, it could be empty. So we might want to allow that. So we actually do not have to insist that the object be non-empty. One of the best jokes I've heard, and you do need a little bit of math to understand this, is the Riemann hypothesis says all the non-trivial zeros of the Riemann zeta function have real part 1/2. And it turns out there's a lot of results that prove how many zeros have real part in a box from sigma to 1 up to height t. And there's theorems about how many there are. And one of my advisors said that what you're basically doing is getting better and better estimates for the cardinality of the empty set. I can show the empty set has at most this many elements. Well, we believe the Riemann hypothesis. We believe there's nothing in here. We can't prove that, but we can get upper bounds on how many things are there. It's a really interesting question as to do you want to allow empty things? In my freshman math book, there was a passage which said, for vector spaces, the empty vector space occasionally screws up some of the results. We will tacitly exclude it whenever it causes trouble. It's better to explicitly state troublesome if the vector space is empty, but I can understand that. So I'm not going to require that I'm talking about anything. It's kind of nice as a professor. I'm used to this. So what's the first thing we want our group to have? Closure. So for the most part, closure is not so bad here. The only thing we have to be careful about is maybe what if we add P to itself? How would we do that? Well, if we add P to itself, we draw the line, we go up to infinity, and then we would come back and we would hit up there. What if we add infinity to itself? We'd still be at infinity. So you just have to worry about those few cases. I'm going to put a check by closure. The point is I want you to realize that I can reduce this to a finite number of things we can easily check. Because it's a cubic, because we have y squared is x cubed plus ax plus b. If I have 2 points R1 and R2 on this, then I must get a third one. So once I have the coordinates of 2 points and I have the y corresponding values, I'll get another point that will be on it. I will have a well-defined point over here, and then I can reflect. All right, so closure is not bad. What's next? Nope. Associativity is actually very hard, so I want to do that one. It's strange. This is one of the only times in life when you don't get associativity for free and you have to work your ass off. That's a technical term, I'm sorry. I just know the calculation, and I don't want to do the calculation. I will post it for you so you can see how bad it can be. What's next?
Inverses.
Inverses. So before we have inverses, we should have identity. And for us, identity is the point at infinity, so that's okay. Now, is commutativity next? Is that a property of a group? No. It turns out that this is commutative. Because how do we do P plus Q? We draw the line connecting P and Q. It doesn't matter the order we add them. We get commutativity for free. So I'll put down here as like a bonus, we have commutativity. So this is one of the strangest situations you'll ever see. Commutativity you get for free, associativity you have to work. The other thing which is nice is the zero vector is not just a vector of all zeros, or the point 0, 0. It's the strange point at infinity, which we got from the projective version. Y squared z is x cubed plus a x z squared plus b z cubed. So now we have inverses. And so, if we take a point over here, let's call this called script p. We want to add something to it to get the point at infinity. And so if we take the point directly above it and add, we draw the line, and the only other point on it is the point at infinity. And when we reflect infinity, we still get infinity. So the point directly above is going to be your inverse. So we do have inverses. And now, associativity. It follows immediately from an advanced theorem called the Riemann-Roch theorem, which you might prove in a complex analysis class or an algebraic geometry class. And then the proof is really trivial and straightforward, and you see what's going on. Sadly, this is a class that does not have complex analysis or algebraic geometry as prerequisites. We do not have the Riemann-Roch theorem available to us. And as much as I like doing asides and diversions, proving that is way beyond what I want to do. Can somebody give me an idea of how to prove associativity? We need to prove it. Can somebody give me a plan of attack? I don't care if it's a good plan. And I know several times in the semester I've asked you guys, I don't care how bad it is, just give me something.
Take 3 points and then just go about it, like do p plus q plus y and then p plus q plus y.
That's going to be extremely painful. That's the best thing I can think of as well. So, brute force for associativity. One of the nice things about having taught for a little over 2 decades is you get a pretty good sense of what students want to see and what they don't want to see. If I am wrong, you can talk to me privately. I'm happy to give you a private lecture going through pages of algebra. I'm happy to just post pages of algebra. I want you to just see that if you do the work, the answer should come. And this is somewhat similar to the proof of Morley's theorem. If the result is true, you should hopefully be able to just slosh through the algebra. Sometimes it's not clear how to rewrite the algebra to recognize the answer at the end of the day. And so one of the theses were on the second reader, there was a result that the student needed and they found on Math Overflow, but without a proof. And they want to know, well, it looks true, so can I use it? Well, we need a proof. And it turns out it's not that bad to prove. You just write cosines as sums of exponentials and expand using the binomial theorem. But then you have to be able to do some algebra and recognize certain things. And that's always one of the difficulties. And so here, what we can do is we take 3 points. So will you accept this as my 3 points? Are those 3 generic points? What else could I have?
You could have 3 points on the circle.
I could have 3 points on the circular part or the oval part. I could have 3 points on this part. I could have 2 points here and 1 point there. What if one of the points is one of the points at infinity? Okay, good. That's actually easy to handle. We don't have to worry if one of the points are the point at infinity. Right? So we have to worry about how we put down the 3 points. Could it matter if one of the points is maybe one of these special points down here? Possibly. So we need to find a formula for what is p plus q. Could some of the points be the same? Yes. So all you have to do is you have to just enumerate all the possible configurations and then just go through each configuration and come up with an addition formula. So what you want to do is you want to have a point maybe x1, y1, x2, y2, and then you'll get some point x3, which will depend on x1, x2, y1, y2, and y3, x1, x2, y1, y2, is you'll get a formula like this. And if you look at what's going on with our cubic, if we know two of the roots, if we know x1 and x2, we can then find the third root. We'll be dividing a cubic polynomial by a quadratic. We then get a value of x. We then find the value of y. We flip it from what it should have been. And then we have to worry about special cases. What if we take 2 points of p that are the same? What would be p plus p? What if we take maybe one of the points over here? You just have to go through all those cases. And then what you would do is you would have your formula that would hold, and then you would have, if I'm in this case, I do this. If I'm in this case, I do this. If I'm in this case, I do this. This should remind you of the 3x plus 1 problem. In the original formulation, if I'm odd, multiply by 3 and add 1. If I'm even, divide by 2. And you have a split definition. And we can have something like this. And then you just go through and you grind through the algebra, and at the end of the day, you see it works out. And then you come over here and you put a check. Now what you can do is you can also try to start drawing this geometrically. Right? If I've got 3 points, so let's say I've got PQ, and I'll put maybe my point R over here. So here's P, here's Q. P plus Q would come here. I would reflect down to here. I then draw the line through these two, which would come over here, and then reflect down here. And then the odds of this working even remotely right now is small. But I could then do R plus Q would be drawing something like this. So I'm coming over here. I come and draw now over here, and then it would reflect down, so not a line. But I wasn't off by a huge amount. Try doing something like that. Okay, so this gives us associativity. So there's a couple of things you could ask. You can ask, what are those formulas? How bad are those formulas? It turns out they're going to be ratios of rational functions. They're not horrible, just a little bit of algebra. So points of order 2. Question? Okay. So I want to find a point of order 2. What that means is I want to find p such that p plus p is infinity. I get to the identity. Or we'll just write this informally as 2p is infinity. So what are my candidates? Well, okay, technically my candidates at every point. Which points do you think might be yes?
Points that are at the circle, edge of the circle, or the...
Yeah. You're going to say oval.
Oval.
Right? So these points here that correspond to y equals 0, those would be my candidates. And if you think about what's going on, the tangent at all these points is vertical. So if I do p plus p and I draw the line through that, I'm going to go straight up. I'll hit the point at infinity. I'll reflect. So these are all order 2. That wasn't so bad. What do you think I might ask now? Yeah. What would be the next natural question to ask? Yeah, so be more specific than greater than 2. What should I ask next? What order should I investigate next? Order 3. I was about to try to make a new Star Wars. That's when you ask, what should be the first order? If I'm remembering correctly. Order 3. So how many people think we should investigate order 3 next? Or is there another order that might be easier? Order 4. So do we want to find p plus p plus p equals infinity, or p plus p plus p plus p equals infinity? Which do you think might be easier? Yeah, I think the line is going to be easier. Because what this means is p plus p, this has to be one of our points of order 2. So can we find a point which, when added to itself, equals one of those special points?
Maybe.
So I mean, I don't want to spend too much time on this. I want to leave this for you guys to think about. But what would it mean to be a point of order 4? Well, it would mean that if I add it to itself, that would be a point of order 2. So then I would have some point, and added to itself, I would have to get this. So if I take any point and add it to itself, I basically reflect downward. Right? So what might you conjecture about points of order 4? Other than these points themselves, which would work. Could there be any new points that weren't points of order 2? Because p plus p has to be something. It's got to be some point q.
It looks kind of like, from the way we've drawn it, that there's a point where it curves up the far right side, where it would come down and hit that third point of order 2.
Okay, so
Like, yeah, right, like a couple inches below where your hand is.
right here.
Yeah.
So if I add this to itself,
Would you take the?
I would reflect down here.
I thought you took the intersection of the tangent line first. Am I thinking wrong?
Let me see. Oh no, sorry, you're right. We're taking the tangent line. So we're taking the tangent line. So you want to say, right? We draw the tangent line here. So if we add this to itself.
Do it in such a way so that it's that third point of order 2.
Oh, could that work?
It depends on what the curvature of that line is.
It depends on what the curvature of the line is. Could there then be maybe one over here that might work? With the tangent.
I don't think so. Oh, well, yeah.
But could the tangent hit that point? Right? Maybe there's a way to take something from here and draw the tangent to the curve. Should there be a tangent to the curve like that? And then this would also come up like this as well. And so if I take this point, add it to itself, I come here and then I reflect. Maybe it's not empty. So how many people think that there should be points of order 4 that are not points of order 2? This one is a little bit harder to think, will the tangent work out over here? But over here, I've got some nice oval. What I can do is I can start off with a tangent line like this that's clearly going to miss. And then I can slowly keep rotating this until eventually it first hits. So I think that's convincing that those 2 points should be points of order 4. The question is whether or not there should be points over here. The other thing is, instead of going through here, where else could the tangent line end up going through?
One of the other two.
One of the other 2. And then the question becomes, how many points of order 4 do you expect? So I'll leave a lot of this for you to investigate. I know this is the end of the semester, things are getting busy. If you want to, I'll make this extra credit. Investigate and tell me, for a couple of elliptic curves, how many points of order 4 do you find? And what can you say about the structure of the group? This is not a group theory class, but this is where you can start to use group theory. One of the goals for this is to get to the point by the end of the semester to show you how elliptic curves are used in cryptography. If I have to motivate why cryptography matters, you do not belong in the major. I think I'm safe saying that. Okay. I hope so, because I just said it and it's being recorded. I'll leave it as we've already sufficiently motivated why we care about cryptography. And if not, several of you had your accounts email me a few days ago with a Google Doc file to open. So, account security is quite important. Okay. I'm going to put a sequence of numbers. So that's a nice start. 5, 6, 7, 13, 14, 15, 20, 21, 20. Oh, I didn't include 22. 22 should definitely be there. 23, 24, 28, 29. Anybody know the sequence of numbers? What would you do? What's your first thought? Go to OEIS, right? Oh, my laptop is now saying an iPad has been detected. I'm quite amazed that it's able to detect the iPad all the way over there without the cable being plugged in. But all right, so I will plug in the first few guys. It was 5, 6, 7, 13, 14, 15, 20, 21, 22, 23, 24, 28, 29. That should be more than enough to have it uniquely determined. And so I will just double check. OEIS says only one sequence found. So these are called the congruent numbers. And I'll include a link to a nice paper by one of my colleagues about some of the history of this problem, where it comes from, and some of the more stuff involved. So it comes down to a very classical problem. Imagine you have a right triangle with rational sides, and you want the area to be equal to n. Actually, let me just double check as to whether or not. I believe all the sides have to be rational, not just A and B. Otherwise, it would be trivial, right? If I didn't require C to be rational, can you construct a right triangle with rational sides to get any integer area if C doesn't have to be rational? What's the area of a triangle? Area is?
This one or any triangle?
Right triangle. AB over 2. And so if I don't require C to be rational, what should I take A and B to be if I want to get an area of n? 2 is one of them, the other one is n. So then every integer would be a congruent number. So clearly I need both A, B, and C as well to be rational, or the problem is trivial. So the question is, if you look over the entire space of triangles with rational sides, which integers can occur as areas? Can anybody give me at least one number that would work? And we call these numbers congruent.
6.
6. Okay. I mean, if this is correct, you should be able to give me a lot of numbers that work. But maybe there was a mistake. I forgot 22 at first. Maybe I put some numbers on that shouldn't be on. My balancer failed. Why does 6 work?
Start with a Pythagorean triple.
Yeah, so if you have a Pythagorean triple, here's 3, 4, 5, 6 will work. What's another Pythagorean triple?
13.
5, 12, 13. And with 5, 12, 13, we get 30. So I'm going to double check it's on the list. It is on the list. Okay. Wikipedia is right yet again. This is a slow way to go about it. Right? But wait. What do we know about right triangles? So let's consider Pythagorean triples. What do we know about Pythagorean triples? Did we prove any results about Pythagorean triples?
We can generate them.
We can generate them. So what does an arbitrary Pythagorean triple look like? Anybody remember? M squared minus n squared. Although maybe those are bad letters because we're having n as the congruent number. Maybe s squared minus t squared equals 2st, and then s squared plus t squared. And if I square things, this will become s to the 4th minus 4 s squared t squared plus t to the 4th. This will be a 4 s squared t squared. So when I add them together, I will get s squared plus t squared squared. So all of my Pythagorean triples are of this form. And so now what we want is oh good, the 2 is going to cancel, right? Because we want, 2st s squared minus t squared over 2 equal n. Or st s squared minus t squared equal n. So the question is, which numbers satisfy this? And there's a lot of algebra one can do. And the goal is to write this in a way that is meaningful. This is one of the hardest parts of number theory. This is one of the hardest parts of mathematics as you go further and further and further. It's how do I write what I'm looking at in such a way that it means something to me and I can do something with it. I think I've already told you the story of Kepler when he was looking at the orbit of Mars. He actually got that the orbit of Mars was elliptical. But he had the formula for the ellipse in a different way than he knew the formula for ellipse. And so he didn't realize at first that he had shown Mars traveled in an elliptical orbit. It's like, crap, I was hoping to show Mars traveled in an elliptical orbit. Instead it travels in an orbit like this. And the orbit was an ellipse, but he just didn't recognize that he had the ellipse. So when you look at this, does this look like anything?
You could factor.
We could factor. We could factor it as s minus t and s plus t. And we could start trying to do algebra. Any thoughts what this might look like? It's going to be some kind of curve in ST space, right? So if we change variables, if we do some transformations and whatnot, it should be able to look like something familiar. Any thoughts as to what that familiar thing might be? Not an ellipsoid. Close. An ellipsoid would be x over a squared plus y over b squared equals 1. An ellipsoid is a quadratic equation. We've got higher powers. We've got things appearing to like third and fourth powers. Based on what I'm lecturing on today, what might you guess? Given that we've spent so much time studying this, what might you guess? Probably an elliptic curve. So there is a change of variables that allows you to pass from this to an elliptic curve. And so if you start with A, B, C, want the area to be 1/2 AB equals n, it turns out this is equivalent to looking at y squared is x cubed minus n squared x. Just double checking that it's n squared. Yes. And you set x to be, I apologize for not memorizing this, x is equal to n a plus c divided by b, and y is 2n squared a plus c divided by b squared. What do you think? How would you check and see if this is true? Just do the algebra. Substitute everything in. So I wrote Mathematica code. I let c equal the square root of a squared plus b squared. I then let n be ab over 2. I let x of ab equal this. Y of ab equals this. I substituted in. I told Mathematica to simplify. You know, I'm a professor. I don't have to do algebra anymore. I have computers that can do algebra for me. I'll share the Mathematica code. And Mathematica chugs through, and what I did is I looked at, you know, if I substitute, you know, in x and y, do I get 0? If I subtract the right-hand side from the left-hand side, and I do. Good, it works. I could do the algebra by hand. It's not too bad, but I don't see the need to do it. So a lot of today is about the value or lack thereof of brute force solutions. So I talked a little bit about associativity. And I said, look, you can improve associativity by brute force, but at the end of the day, do you have a better understanding of associativity? Do you have an understanding of where it comes from? No. But now, do I really have to justify associativity to college students in a math class? You basically assume almost every operation you have is associative, that you can be careless about your parentheses. Right? Is it surprising to you that something is associative? No, it kind of feels reasonable. I'm adding things, I'm drawing lines geometrically. It probably doesn't really matter which way I do it. Although the fact that I'm drawing lines, and now I check these two first versus these two first, I now have different sets of lines. So there is real meat, there is real content to associativity. This is one of the reasons why I like showing this problem right now. Is it at all clear where the hell this comes from? Yeah. And I'm double checking right now to make sure that I haven't made any mistakes in putting the transformations on the board. No, good. Is it at all clear where this comes from? No. Does this give you any idea how I could pass from my right triangle to this elliptical curve? No. But if you just do the brute force plug and chug algebra, is that enough to verify that this is correct? Yes. So you will be in a position where you can use this transformation without understanding where the hell it came from. And if I gave you a slightly different problem, what if I decided, you know what? That factor of 2, I don't really like that factor of 2. I want twice the area to be an integer. Would that make more numbers or less numbers congruent? We'll call this, I don't know, 2 congruent, where I want twice the area to be an integer. So would that make more numbers or less numbers become congruent? Yes.
I think more.
More. If you were an integer before, then when you multiply by 2, you're still an integer. So all the 2 congruent numbers, they will clearly contain all the congruent numbers, but they will contain more numbers. Which other ones? How would we go about seeing that? Would you be able to figure out how to generalize something like this? It's not clear. You might have some guesses, but that's one of the problems with something like this. So it all comes down to, can I find an x and a y that work? And so if I can find an x and a y that work, if I can find a point on this elliptic curve with rational coordinates, can I then find A, B, and C? So this is one of the two major tricks in Calc 3. It's the change of variables. It's converting to a system that's better. You see this in linear algebra. You choose the basis that's better. As a Bostonian, there's only one nice thing I can say about a subset of New York. Which subset of New York must I say something nice about, and why? Be very careful with your answer.
Stadium?
No. Who here has traveled in Boston? Where you'll have things like, Comm Ave and Beacon that would cross like this. What part of New York is much better? Manhattan. As a Bostonian, I have to admit the grid system in Manhattan is very nice. It is a very good coordinate system to move around. The Boston coordinate system is a nightmare. Okay? Linear algebra is all about changing coordinate systems for what works best for your problem. Over here, I'm changing coordinates from the x, y of the elliptic curve to the a, b, c. Oh wait, I've got 3 coordinates. But when you look at the elliptic curve, all I want is a, b, and c to be rational. So maybe I've got some freedom in terms of rescaling. But I also have the value n. So if I give you n, x, and y, should I be able to get a, b, and c that are rational? Let's go the other way. If a, b, and c, and n, if a, b, and c are rational, will x and y be rational? Yes. Then the question becomes, if x and y are rational, will a, b, and c be, if x, y are rational and n is an integer, will a, b, and c be rational? Now what's nice is I have this quantity a plus c over b. I have a plus c over b times b. So the first thing is I can clearly get a plus c over b is going to be a rational number. And then I'll get 1 over b is a rational number. So I'll get b is a rational number. So now I know b is a rational number. And now that I know b is a rational number, I should hopefully be able to get both a and c are rational numbers. So I'll let you go through and do the algebra to show that this will give you rational numbers for a, b, and c. So there's a one-to-one correspondence that I can study in an a-b space, or I can study in an x-y space. There's another way that you could look at this. How could I rewrite x cubed minus nx squared? How might you rewrite that? And I deliberately do not want to write it. I want to see how you would rewrite it. This is all about the power of looking at things the right way. How would you write x cubed minus n squared x? You look like you're close to saying something.
X times x squared minus n squared.
So x times
X squared minus n squared. And then you capture that.
okay, so now give me the next line.
X times x plus n x minus n.
Does anybody have any other ways of writing this? You're close to how I would write it. You have 3 factors. How many ways do you have to order the 3 factors?
6.
6. Do you want to do it as x, x plus n, x minus n?
You could put x plus n first.
You could put x plus n first, or you could put
X minus n first.
yeah. Which do you want to do? I would do x minus n. How can you interpret this? So I've got 3 numbers, x minus n, x, and x plus n. what can you say about how these three numbers lie?
Evenly spaced.
They're evenly spaced. This is a 3-term arithmetic progression. So what I'm asking is, can you have a 3-term arithmetic progression where the product of the three numbers is a perfect square? Now I have been very vague, and so it's quite possible that something I said might be a little bit wrong. You would have to go through and put in the actual details and do the calculations. Maybe when I'm trying to push things through here, maybe I need more than just x and y rational. Maybe I need x and y to be integers. Maybe I don't. You need to do the algebra. The way you learn things is by rolling up your sleeves and doing the algebra. So this is either a 3-term arithmetic progression centered at an integer, or a 3-term arithmetic progression centered at a rational with an integer spacing. And the question is it possible to have a product of 3 terms in an arithmetic progression being a perfect square? And it turns out this happens to be connected. And so it all comes down to, if I give you an elliptic curve, can you find a point on the elliptic curve with either rational coordinates, or maybe more strongly, with integer coordinates? How do we find that? And so we've already shown that the points on an elliptic curve form a group. We can add them, it's a commuted group, it's very nice. You can look at the subset of points with rational coordinates. And what's really nice is if you have 2 points with rational coordinates, then the line, the third root is going to be rational. And the value of y will be rational. And so it turns out, because it's going to lie on the line, so the line has rational slope. So the subset of points that have rational coordinates form a group themselves. And you call that group EQ. E stands for the elliptic curve you're looking at, and Q is the points with rational coordinates. And this forms a commutative group. And the question is, what is the structure of this group? And this comes back to what we were doing at the very beginning of the day. Do you have to have an element in your group, or can your group be empty? I want to be able to say to every elliptic curve, I can associate a group, the group of points with rational coordinates. It may be empty. There may not be any points on the elliptic curve with rational coordinates. Trying to understand the structure of this is one of the biggest open problems in all of mathematics. This is related to what's called the Birch-Swinnerton-Dyer conjecture. And I'll talk a little bit more about this, but we'll probably follow the textbook a lot more closely on Monday about how you actually deal with finding points on an elliptic curve with rational or integer coordinates. How can you find them? Here's one reason we might want to find them. We're just curious as to which numbers are congruent. Most of us probably don't care if a number n is congruent or not. Who cares if the area of a right triangle with rational sides is an integer? But the techniques are very nice. I will just say, since we've done it in other places, one other way people prove certain numbers are not congruent is by Fermat's method of descent. So there's a lot of good mathematics related to all of this. If you haven't picked up the exam, please do so. It is due on start of class on Monday.